Yeah, another property of light when it hit the interface is the attenuated total refraction. In previous section, we learned that when the light is sent to the interface at an angle greater than critical angle, and then uh, total internal reflection may occur, but close inspection of the phenomenon, and then the people found the total reflective uh, light intensity is a little bit, although very small, a little bit attenuated. Yeah? A little bit attenuation means decrease, okay, weakened. Okay, here, even though light is totally refracted, the electric field of the light penetrates uh, the cladding to some extent. That light is called evanescent wave. Evanescent means fade away. Okay, and as I said, using the total reflection, we can we can make the waveguide. Okay, waveguide is a planar layer in which light is totally reflected. Okay, and one waveguide, waveguide of reflective index is greater than the n2 of surrounding uh, the material. The sine theta critical angle is n2 over n1, right? And look at this figure. Okay? Here, the light is sent to this interface between this medium, and this medium. Okay, the refractive index of this medium is n1, and this is n2, and n1 is greater than n2. Okay, here at the interface, okay, the all the light intensity may be totally reflected here, okay, but the sum of electric field now leaks um, toward the this medium 2, okay. This is electric field, okay, and this electric field, not all of them is reflected, but some of them is present in opposite side, okay. Yeah, that's called attenuated total reflection. Yeah, total reflection is okay, but intensity is a little bit attenuated, okay. And this wave, okay, on the other side is called evanescent wave. And then this electric field decreases with respect to the distance, and then uh, the equation is this one, okay. This electric field E equals E0. Yeah, E0 is the original incoming electric field intensity multiplied by exponential minus x over dp. X is the uh, distance from this interface to the other side, okay? And dp is the characteristic this decaying distance, okay? So dp is defined by this equation, okay? This equation is rather complicated, so I don't know, how the people, the researcher, derived this equation, or the physicists, do that, okay? This is called penetration depth. Yeah, this is exponentially decreasing, but this is a representative penetration depth. For example, uh, and the light whose wavelength 140 nanometer uh, instant, yeah, to the interface, yeah, and at 70 degree, all right, and N1 is 1.7 and N2 1.45. Okay, I'm sorry. And let me see. This one about 140 nanometer. Yeah, I think that's the penetration depth. Okay, just a second. Okay, I'm sorry. Yeah, I forgot. Let's continue. Okay, and at the angle of 70 degree, and if you send 590 nanometer wave, the light, and then this penetration depth is about 140 nanometer, right? Very short. Okay, it's beyond this distance is rapidly is exponentially phase out. Okay, and this is enough to allow the light to interact with the many layers of molecules like protein. But the beauty of this phenomenon is that if you coat at the other side, yeah, you coat here with biomolecules such as protein, but that the protein side is much less than uh, this 140 nanometer, right? So this evanescent wave now what the monitor detects the biomolecules on the other side. Okay, isn't that wonderful? You send your UV or visual light on this side, and then your sample is coated on the other side. But this sample can be monitored by this wave. Yeah? That's the beauty. Okay, so this attenuate total reflection has been applied in many ways, and this is the what uh, used as a detector. Okay, here is the this is I think the separation instrument, and then here the important part is that this one, this liquid now comes out from this port 5, and then it enters one end of the detector, and then this one it contains this liquid contains the component of your interest, and then it passes through this part. Okay, and then uh, it goes out. And here, although this liquid is flows on the other side, and then now you send your light from from this prism. Okay, yeah, this is expanded version. Okay, now sample passing through this layer, and then you send this light, and it reflected inside this prism many times. Yeah, diagonal is 3 times, but I think it's many times. Okay, and your sample you here this this dot, right? When your sample is within this penetration depth that can be detected by this wave, and here you only detect, yeah, this one, this light, and then this light conveys the information about of your sample. Okay, yeah, this is a beauty. Yeah? So this one, this type of configuration is very widely applied to the uh, Fourier transform infrared spectrophotometer. Okay, yeah. So this way, um, the caffeine has been detected. This is just one example. Okay, and you see, this is the IR spectrum, IR absorbance, and uh, using the attenuate total reflection, yeah, ATR mode, you can very nicely detect it, this caffeine, the spectrum, okay, spectrum. But in water, this caffeine, the spectrum is not very distinct, okay, very wonderful. And I think this is the last one. Well, different optical phenomenon, which is a surface plasmon resonance. Yeah? This phenomenon is not very easy to understand. You know? But using this phenomenon, SPR, people constructed the sensors. Okay, what is the surface plasmon resonance? All right, conduction electron in a metal is free to move. All right, that's the properties of metal. Inside the metal, there are a lot of free the moving electrons. Okay, within metal in response to applied electric field. Okay, electrons are freely moving when the electric fields are applied to the metal. Okay? Surface plasma wave, that is called surface plasmon. This is an electromagnetic wave propagating between metal and dielectric insulator. Okay, look at that. This one. This is the uh, gold. Gold is coated on the surface, and here is a chemical sensing layer, and then you send your light from this side, and it's reflected from the gold surface. Okay, surface plasmon is the collective motion of electrons in gold. Okay, and this surface plasmon, actually surface plasmon is a collective motion of electrons at the interface. Okay, so surface plasmon is really sensitive to the surface. Okay, it propagating between metal and dielectric insulator. This metal and dielectric here. Okay, and electric fields, using the electric fields, you can detect the surface, the what this reflectivity of this light. Okay, anyway, you simply remember the surface plasmon is the collective motion of the electron at the surface. So this one is very surface sensitive technique. Okay, so but the peculiar is that notice the surface plasmon is excited, excited um, by the electromagnetic wave. Okay, here look at this figure. This is x-axis is the angle of instance. Okay, theta, and y-axis is percent reflectivity. Okay, then now you measure the reflected intensity while you change this instant angle, okay, very minutely. Okay, here look at that. This one, this solid line, and you scan from the 50 degree to higher degree, and around at the 52 or 52.5 degree, and then the reflective intensity, yeah, becomes, suddenly is around 100%, is rapidly decreasing. Okay, and then it reaches the minimum, almost a zero reflectivity. So at this angle of instance, then there is no what, light detected. Okay, because of surface plasmon. In this case, yeah, gold surface plasmon now absorb this incoming light at this particular angle. Okay, at this particular angle, and then if you increase, then this reflectivity also increases. Okay, so this one is characteristic of surface plasmon resonance. Okay, so if you set this angle here, then you can make a surface plasmon resonance. All right, yeah. And how do this phenomenon um, apply to detect the molecules of your interest? Yeah, interestingly, you know, the other side of gold is coated, for example, with polymer here, right? And then surface plasmon resonance angle changes very little. Okay, the pattern is the same, but when the gold surface of the other side is coated with foreign species, then surface plasmon or resonance angle a little bit changes. Okay, not much, much less than 1 degree. Okay, so by measuring this one angle change, you can have information about the species coated on the other side of this in this case a gold surface. Okay, yeah. So look at this this value. Now commercial instrument There are commercial instruments for surface plasmon resonance measurement, right? And then, very amazingly, usually people use a laser beam, right? The the degree, this angle change of 10 to minus 4 to 10 to minus 5 degree can be detected, right? This is amazing, right? This is amazingly small degree, but at any rate, it can be detected, all right? Yeah. As data increases, okay, the incident angle increases further, surface plasma is set up, okay? It's a surface plasma resonance, absorbing energy from instant light by both layers. There is a small range of angle. Yeah, this range, angle range is very small, but it can be detected by modern technology. All right. The plasmon is in resonance with instant angle. Okay, this plasmon, surface plasmon, that's the collective motion of electron on the surface, um, is in resonance with instant angle. Okay, in which the reflectivity becomes minimum. Right. So here is an application of the surface plasmon resonance. Okay. Now you coat, usually the gold is used for the surface plasmon resonance experiment. You coat, the gold with these molecules. Okay, and then you add DNA biotin. DNA biotin is this kind of species. Here is the structure, right? Then you bind this butene to DNA and wash away, yeah, to remove the non-complementary DNA, and then you here, since the complementary DNA is connected to the butene, and then it makes a double strand, okay, and then surface has been changed, right, upon this one, this material, yeah, okay, this one, DNA butene, this molecule now um, bound to the surface, and then surface plasmon angle changes. All right, yeah, this here is an illustration, and then after you attach it, this one, butane, and then abidine, streptabidine, right? This one. Uh, Now specifically, you see, you know the shape. This is specifically this abidine, okay? In this case, streptabidine is bound to the surface. Yeah, this interaction is specific, and then surface plasmon changes. Okay, this is result. This one, this solid black line, and the solid dotted line is the gold surface modified with PNA, and gold PNA hybridized with DNA up to this point. Surface plasmon change is very very small, but when you add this streptabidine, yeah, and then the plasmon resonance angle changes a lot here, right? This blue line, a lot, by a lot I mean very small angle. Okay, look at that. This angle is just less than 57 degree, and this one is just more than 57 degree. Yeah, this small angle difference um, can be precisely detected. Yeah, so by monitoring this surface plasma resonance response, you have the information uh, on the surface. Okay.